This is lecture 9, part 1. We're going to go over some basic techniques to do proofs on sets. The technique we're going to talk about in this part of the lecture 9 is about element-wise proofs, prove set equality, prove biconditionals involving set equality, and we're going to look at theorem 6 from the textbook regarding properties for set operations. And you'll notice those operations look very similar to some of those Boolean operations, which is theorem 2 from chapter 2. And finally, we're going to talk about duality. All right, so the first thing we're going to look at for any proof involving sets is talking about element-wise proof. Essentially, if I want to show one set is a subset of another, we want to show that every element from the first set must be an element of the second set. For example, if I want to show the set A is a subset of the set B, then we want to say for all element X in A, we want to show it is in B. Okay, so let's try this with a simple example, and I'm going to write out a sketch here. Again, this is a good time to pause the video and see if you can solve this by yourself. Okay, so what I want to show here is assuming A is a subset of C, B is a subset of C, we want to show A union B is now a subset of C. Okay, so what you want to show is essentially you want to show one set is a subset of another. Remember, then what we want to show is if we have an element from the first set, we want to, for any element X in the first set, we want to show it's an element from the second set. All right, how do we do that? So our goal is to show for all element X that is in the first set, it's in the second set. Okay. So there's two cases. Now, if you look at X belongs to A union B, by definition of set union, you have two cases. Because X is in A union B, case number 1 is X is in A, case number 2 is X is in B. All right. Okay, in case number 1, X is in A, then because as part of the hypothesis, because A is in C, then by definition of set subset, then X is in C. That's it. Okay. X is in A because A is a subset of C, then X is in C. So we have already proved the conclusion. Now, what we want to look at is to say, well, what if X is in B? Because we know there's another condition we have not used from the hypothesis, which is B is a subset of C. A is in B, B is a subset in C. Then, by definition of subsets, X is in C. So that is exactly proof. Okay. Of course, let's look at a more detailed proof. We spell things out. This is how you provide the more accurate description of the proof. But the idea really in this proof is to use the condition, which is a hypothesis, in the problem itself, which is, you know, A subset of C. So if X is in A, X is in C. B is a subset of C. So if X is in B, X is in C. Okay. So it's not too hard to prove this element-wise. Now let's look at the next question. We want to show about specific two sets when the union is equal to the third set. So what are those two sets? The first set is what I will call set A. This is all the elements who can be expressed as 4k plus 1. So in other words, this is a set of integer when its mod 4 has a remainder of 1. Or in other words, if I take the quotient the quotient is k, the remainder is 1. This one is all the integers, where if I mod 4, the remainder is 3. This is all the odd integers. Okay, so now if we want to show A union B is a subset of C, then we have two cases, right? The first case is if X in A, we want to show X is in C, right? Because when I say X is in, so I take a X, which is part of A union B. If I want to show this element is in C, X has two conditions, either is in X or is in B. Either is in A or is in B. The second case is if I want, when X is in B, we want to show that X is in C. Okay, let me write it more accurately. So for the first case, when X is in A, you want to show it's in C. Now we need to use a hypothesis X is in A. Because X is in A, everything I wrote here is, of course, a sketch. If X is in A, X can be expressed as 4k plus 1. I want to show it in C, so I need to have it looks like the form in C, which is 2 times some integer plus 1. To arrive at that, the easy way is to factor out 2. So if I factor out 2, this is 2 times 2k plus 1. And by closure property, if I let n equal to 2k, by the closure property of integer under multiplication, this is an integer. So x is equal to 2n plus 1, right? It takes a similar form as the element in C. Therefore, x is in C. Now, for the second case, when I assume x is in B, x can be expressed as 4m plus 3. I want to arrive at the form that looks like 2n plus 1. What do? I do factorization, factoring by 2 again. But in this case, I want to arrive at the form that's represented as an odd integer. So I'm going to do a little bit trick. I'm going to say 3 is equal to 2 plus 1. And then now I can factor out 2. This is equal to 2 times 2n plus 1 plus 1. Again, I'm going to use the closure properties of integer. I'm going to let the variable n equal to 2n plus 1. And by closure property, this is integer. So that means x can be expressed as 2n plus 1. Again, this means x belongs to C. Okay? Well, in here, I have skipped a lot of sort of connecting words. In order for you to write this carefully in homeworks or exams, this is how you would write it. Of course, I use some simplification of set capital A, B, C to represent the set, but the main idea is the same, right? So under case 1, when I want to prove that set, every element in set A is part of C, you want to first use the set membership to express the element x to be 4k plus 1. And then you use distribution property or factorization to factor out the 2. Then you use a closure property of integer after multiplication, and you express it as what it is. So this is really the detailed proof with respect to the previous sketch I just given. All right. Next type of proof you're going to see for sets is proving set equality. Essentially, when I want to prove two sets, A equal to B, what you want to prove is A is a subset of B and B is a subset of A. In other words, that those two statements are logically equivalent. Right? So if I give you a problem like this, to prove that the set on the left-hand side is equal to the set on the right-hand side, what you need to prove is you want to show essentially the set on the left-hand side is a subset of the set on the right-hand side, and the set on the right-hand side is a subset of left-hand side. Okay? So what is the case? The case number One is going to be a left-hand side. You want to show left-hand side is a subset of the right-hand side. Okay. And then case number 2. Oh, actually, let me give it more space. Case number 2 is the right-hand side. You want to show the right-hand side is a subset of the left-hand side. Okay. So now each of this problem reduced to prove set membership. So you can do element-wise proof. So that's what I'm going to do. If I want to show, I'm just going to show case number 1. If I want to show the set on the left is a subset of the set on the right, you just take the element on the left and show it belongs to the right. So let the element X that belongs to the left-hand side. Okay. All we need to do is to use a bunch of properties involving set union and set intersection. For example, what are some of those properties? If X belongs to A intersect B, what does that mean? That means X is in A and X is in B. If X belongs to A union B, that means X is in A or X is in B. If X is in A, which is a set, X is also in A union any other set, right? When union any other set, I just increase the size of current set, but X is already in the current set, so this is also true. So those are some of the properties you might use involving intersection, union, and other set operations. So in this case, assuming X belongs to the union of A intersect B and A intersect C, what does that mean? It means X is in A intersect B or X is in A intersect C. So those are two subcases. Okay. And now when X is in A intersect B, what does that mean? That implies X is in A and X is in B. All right. Because X is in A, what do I have? Did I get it right? Oh no, actually, sorry, just a sec. Yes. Well, X is in A and X is in B. This part implies X is in B union C. This is using the third property I listed above, right? If I enlarge the set B by B union C, X is still in it because X is already in B. So now I have X is in A and X is in B union C. What does it imply? This implies X is in A intersect B union C, which is what I want to prove. Okay, and then case B is the same thing. X is in A intersect C, that means X is in A and X is in C. Because X is in A and X in C implies X is in C union B, which is equal to B union C. Again, because X is both in A and B union C, it's in their intersection. All right. Okay, that is for case 1, and case 2 can be done similarly. So I'm not going to go into detail. If I want to spell it out, this is sort of the detail of the proof. Remember, there's 2 parts. If I want to prove the 2 sets are equal, I need to prove the left-hand side belongs to a subset of right-hand side, and right-hand side is a subset of left-hand side. Okay. And of course, for this particular state, in order to write it carefully, you have quite a bit of cases. Okay. Now, we want to prove if and only if condition. Okay. So again, I'm going to give you a sketch, and this is a good time to pause the video and see if you can solve this on your own. So we assume we want to prove A is subset of B if and only if, which is a double arrow, A intersect B is equal to A. So because it's a double arrow, when you prove it, you need to prove each of the direction of the arrow. So let's say the first part, what we call claim number 1, is to say that if A is a subset of B, we want to show A intersect B is equal to A. The claim number 2 is show the other direction. Show if A intersect B is equal to A, that A is a subset of B. Okay. So let's do the first part together, and then the second part you should try to do it on your own. So the first claim is to show that if A is a subset of B, then it implies A intersect B is equal to A. Before we prove that, let's have a mental picture. Let's say this is a set B. This is a set A. What does this mean? If A is a subset of B, if A is a subset of B, which is on the outside, then A intersect B is A. So that means the intersection between those two sets is a smaller one, which is A. So intuitively, this seems to be okay. Of course, I want to draw the universal set. So how do we prove that? Because, let's see, A belongs to B. Okay. So I want to show A intersect B is equal to A. So I want to essentially show two parts. Part 1 is A intersect B is a subset of A. Second part is A is a subset of A intersect B. That's where you get equality between these two sets. Okay? The first part is fairly easy. It says if I take a set A, take it the intersection with another set, which shrink the current set, it's a subset of A. Okay? So this is easy. The difficult part is the second part. Is I want to show if an element is in A, it's also in A intersect B. So what do we have? So let X be A. And because A is a subset of B, this means X is in B. So now X in A, X is in B. That means X is in A intersect B. So I just showed A is a subset of A intersect B. So that's it. Okay. So what's the large picture of this problem? You have, because it's an if and only if statement, you need to prove the direction in both arrow direction. And for each of those, that's what we call claim 1, claim 2. For claim 1, I need to show set equality. Then I need to show that the set on the left is a subset of the set on the right, and vice versa. Okay. So let's go over the detailed proof together in more sort of formal way. So because I want to prove if and only if condition, the claim number 1 is going from left to right. So when A is a subset of B, we want to show A intersect B is equal to A. So this has two parts, as we mentioned before, because I want to show this two set element. The first part is to show A intersect B is a subset of A. The second part is to show A is a subset of A intersect B. All right. So, and for each of those parts, we need to use essentially definition of set intersection. Okay. We assume we start with the element X that is in A intersect B. By definition of intersection, that means X is in A and X is in B. Because it's in both, it's in their intersection. Okay. And again, by definition of subset, well, it's in the intersection, it's also in A. So the intersection is part of intersection of A intersect B is part of A. So this is actually what the step where I say this is the easy part. Okay. The slightly harder part is to show if an element is in A, it's also in A intersect B. And this is using the property, I start with the element in A. Because A is a subset of B, that means the element is part of B. Again, using the definition of intersection, because X is in A and X is in B, that means X is in A intersect B. So what does this mean? That means when I start with element in A, this element is also in A's intersect B. This is by definition of the subset. So A is a subset of A intersect B under this assumption. So now I just only prove claim 1, which is the arrow going from left to right. I also have to prove the arrow going from right to left, which is if A intersect B is equal to A, then A is a subset of B. So in order to prove A is a subset of B, I start with the element in A. I want to prove it's in B. So I start with the element X is in A. Because by hypothesis, A intersect B is equal to A, that means X is already also in A intersect B. Now use definition of intersection, X is in B. So this means X in A eventually leads to a conclusion X is in B, which means A is a subset of B. So now once you prove the two direction, the if and only if, you get the final result. So the next thing that is kind of interesting is you're going to see what we call theorem 6 from the textbook, which is basically a bunch of properties for set operations. And this is going to look quite familiar if you compare this with logic operations. Remember, in logic operations, if I have P and Q or logic statement, I have P and Q is equal to Q and P. That is commutative property. And then P and Q and R is equal to P and Q and R. This is an associative property, so on and so forth. So you can actually sort of see the similar set of properties associated with pooling operation show up as properties for set operations. For example, a set A intersect B is the same if I switch the order, which is equal to B intersect A. Or if I take union operation, A union B is equal to B union A. We have associative property so that A intersect B intersect C. If I take the intersection first, involving A, B, and then C, is the same as taking the intersection involving B and C first, and then intersect with A. So that associativity, distributive property is the same. So if I distribute operation of A intersect B union C is equal to A intersect B, A intersect C, and take the union zone. And you also have something similar, essentially, we also call it actually De Morgan's law. If you take the complement of the set A intersect B, you get A complement union B complement. The important part, in fact, in this case, let's use, is actually when you take the complement you change the direction. If you recall the De Morgan rule for P and Q negation, you get negate P or negate Q. Again, we kind of change the direction from and to or, and later on from or to and. Okay? And similarly, you have a few extra properties, which is taking a sort of complement or difference is similar to negation. So everything is in A, not in B, is equal to A intersect B complement. Again, to understand this, it's good to have a mental picture. Everything is in A, not in B, is this yellow part, but you can also draw A intersect B complement, and that is the same area. So this is just using Venn diagram to illustrate the equality. So now we want to use theorem 6 to prove some equalities. Okay, so this is what you need to do. Okay, so this is where you want to pause it for a minute or so, and then try to solve it yourself. And what I'm going to show you is how we go around the solution in the next stage. Okay, so how do we solve it? If I see this property where the starting point is A union A complement intersect B. So this looks very much like De Morgan's law. Not De Morgan's law, distributive property. So that's exactly what you do. The first step you apply is distributive property. You take, you distribute the operation. So A union A complement intersect B is taking A union A complement and intersect A union B. So pretty much afterwards, it seems to be pretty straightforward because the next step you see is when A union A complement, this is using the negation property, this is really A union A complement is the entire space, because if this is A and this is universal set, everything inside A is in yellow. Everything outside A, which is complement, is in blue. And if you take A union A complement, it's the entire universal set. And now if you take universal set and intersect with set, you can also use one more rule of commutative property to kind of switch the order. And then when you take a set intersect with universal set, is the set itself. That is using identity property. So that is what you get for this proof. Okay. So the difficult part of this proof is essentially the first step, using the distribute property. Okay. So now we want to use, want to prove that if A belongs to, is a subset of B, then A union B is equal to B. And this one we're going to give you a hint, meaning that in the earlier part, we have proved, in the earlier part of this lecture, we have proved that if A is a subset of B, then A intersects B is equal to A. So you can use this property directly, but then you want to use this property in combination with theorem 6. Okay. Again, this is a place where you can pause the video and we can do and then try to solve this on your own. But I'm going to go ahead and start the proof. Okay. So keep in mind the hypothesis of those two things are the same. Is A a subset of B? So assume A is a subset of B. I want to prove that A union B is equal to B. So I want to go from left to right. So what do I do? Okay, in this case, so I start from the left. A intersect, oh, A, I want to show the left-hand side is equal to the right-hand side. So I start with the left-hand side, A union B. Because A is a subset of B, then A intersect B is equal to A. This is just using substitution. Then I'm going to substitute A by A intersect B. Okay, so now what do I have? I have A intersect B union B. Now the next thing I want to do, so this is by substitution of this property here. Now what I can do, maybe I want to rearrange it a little bit using commutative rule. So I can say this is equal to B union A intersect B. This is just okay. This is just commutative rule. And now I'm going to use distributive rule. The distributive rule is this one, okay? This is equal to intersect B union B. Okay. So what do I have? I have B union A intersect B. Where am I? Let's see. B union B intersect A. Oh yeah, actually, sorry. Let me clear it out a little bit. I shouldn't use absorption rule. Here, this is just commutative rule. But then I'm going to do one more. Yes. So this is just simply absorption. Okay. So actually, I shouldn't use distributive rule at all because that's actually making it more complicated. But in fact, here I have B union B intersect A. This is just absorption, which is right here. Okay. So as you can see, I also sometimes get stuck. This is equal to absorption. This is B. Okay. All right. So the last bit I want to mention is called duality. So it's a similar thing where the dual expression can be done through some exchange where we switch union operation by intersection operation, and then you switch the universal set with the empty set. So if I have the expression A union A complement intersect B is equal to A union B, then the dual is by switching each of the symbol, union symbol by intersection symbol by union symbol, and again, union symbol by intersection symbol. So what does this mean? This means if I have the expression, the first expression here, let's call it expression 1, and that involves two expressions. If I replace each of the symbol in there, say union, replacing union by intersection, replacing universal set by empty set, then the resulting dual expression is also true. Okay, so we're going to see some examples later in proofs where we can use duality.